All right. Well, it's 9:30 and we're still missing about 10 people. Good morning, everyone. We're getting to the end of chapter 10. You already received homework number 2. So once we do that, then about 10 days later, most likely we're going to have second test, which is chapter 10 only. Now we're going to talk about cogeneration. The whole concept of a cogeneration is producing power, actually producing two forms of energy, producing power and process heat. Almost every large campuses have cogeneration plan. Cogeneration plan is the most important part of this chapter, and it's a very important thing that we use all over the United States and all over the world, basically. The entire concept is we generate power from our cycle, we recover some leftover heat from the cycle, and use it for another purpose. Now we can use that heat to generate cooling. And I designed that in several places, especially in LA Harbor College. You can go and see the cogeneration that we generate power and we recover the heat and convert it to cooling through absorption chiller to cool up the campus. I have designed cogen for large manufacturing food processing facilities to recover the heat, generate the steam, to use it for the cooking and whatever they were doing in food facilities. There are lots of applications in cogeneration. Almost every airport has cogeneration. Every refineries, without exception, have cogeneration plant. As I said, most of the hospitals today have cogeneration plant. Most of large university campuses have cogeneration plant. So it is very important. And I want you to pay attention to what I'm going to do here. I'm going to do an example. But the important part is remember all the details that I'm doing, because that could be on your final exam. So please pay attention to it. Now, there are so many ways that we can do cogeneration. There is no just one way. There are a few examples in your textbook that's going to be totally different than the one that I'm doing here. The one I'm doing here is the most efficient way of doing a cogen. So I want you to focus on that. And if I give you a problem in your final exam, most likely it's going to be, 100% guarantee it's going to be exactly like the one that I'm doing here, not the one on your textbook, not the one that you probably have seen somewhere else. So please pay attention to this. Now, let's do the diagram. Diagram is very simple. Again, we have our boiler. That's our turbine. I extract some of the steam from the turbine and I put it in a box. I call that process heat. And I tell you what that is. Of course, we're going to have condenser here. That's our source of water. This is first pump. Here I talk about it. That's our second pump, and going back to the boiler. From one, going through the pump, we come out at point two. Now here, this would be point three. This is point four. This is 5, 6, and this would be 0.7, and finally, this is our 0.8. Now, this is called mixing box. This mixing box, what it reminds you of? I extract the steam, coming here, I recover the heat, and the balance of it goes to this box. The cold water come here, get mixed with that balance, which has a higher temperature, and goes out at this point. This looks like open feed water here, right? The whole concept of open feed water heater, or mixing the steam with cold water to get a hot water, taking it to the boiler. And that's exactly what I'm doing here. Simple as that. Now, as you can see, whatever that I extract on this turbine will come out at 0.3. So 0.7 and 0.3 have the same mass. M3 is the same as M7. Now, what's this is the workable pump 1 that I put into the system. This is a workable pump 2. Of course, this is the Q in. This is workable turbine. And we have 2 of them. This would be my Q out. And this, we call this Q process. You notice that I put a large Q because in the cogen plant, you always get in a mass flow rate. So all of this going to be big Q out, big W turbine, big Q in, big workable pump, 1 and 2. Now, we take this heat and we send it out of the cycle to be used for another, another thing to do with it. As I said, this could be used in a manufacturing process. This could be sent out to generate cooling. This could be sent out in case of a hospital. For instance, you can use this heat to generate steam to do the laundry and, in the facilities, because in the hospitals, their laundry system is very sophisticated because of all the germs and microbes and everything that is there. So they use a lot of steam. Water wastewater facilities, they have this cogen. They use this process heat to generate the steam and remove the sludge to separate the solid and the water, so they can process the water and wastewater and collect this, the solids, and send it out to be used as a fertilizer. And they process the water side of it, and they dump it in the ocean. After they process it, they just don't dump it, the way it is. So, for instance, I designed a cohesion plan for two high schools in Power Unified School Districts. Power Unified School Districts is two high schools. They had Olympic-sized pool. And by the rule of the Olympics, the temperature of the water has to be 81 degrees Fahrenheit throughout the year. Because a lot of people will go there, practice 3-4 years, get ready to go and compete in the Olympic. So before, they had a big, huge, boiler to generate this, hot water, mix it with the regular water, and they had a problem keeping it at 81 degrees Fahrenheit all the time. So what I did, I designed a cogen. We generate some power, much cheaper than they were buying it from local utility, and we recover the heat, and we dump that heat in the pool, and we got rid of the boiler. So you can see there are a lot of savings involved. They don't have to deal with the boiler, they don't have to maintain it, they don't have to operate it, they don't have to pay for the gas to heat it up. All of that was the savings for them. So they got the power at a cheaper rate, and they got a free heating that they use it to heat their pool. That's why the cogeneration is the most popular thing in our industry. Well, you see it everywhere because it's extremely beneficial when it comes to, environmentally and as well as, financially. Every large facilities have this because they buy the cheaper power and they use the free heat to do it something else with it. So we generate this heat. Once we generate this heat, will go outside of our cycle to be used for another purpose. That's a concept of a cogeneration. I'm generating power, that's one form of energy, and I'm doing the process heat, that's another form of energy. That's why it's called cogeneration. Now, there are a few things we need to pay attention. This is M6. M6 will come in, split to two. So you have M6 is equal to M7 plus M8. Now, M8, M1, and M2, they're all the same, right? So M8 is equal to M1 is equal to M2. M7 and M3, as I said, are the same. So M7 equal to M3. Now, M3 will split to two. It comes here to this box, M2 goes to that box, M4 goes up. So we have M2 plus M3 is equal to M4. Then when it comes here, M4, M5, and M6, all the same. So M4 is equal to M5 is equal to M6. You don't have to remember any of these. Just by looking at it, you can see where the masses are the same and where are the splitting. So our focus is going to be here as far as the change of the energy concerned. Because this is open feed water heater. So what comes in, the energy that comes in, which is M2H2 plus M3H3, has to be equal to M4H4. So by rewriting this, I can write it M2H2 is equal to M3H3. That has to be equal to M4H4. And you see the importance of this when we get them. Now, there is another thing that is important to know. I'm going to just use some arbitrary numbers. So I want you to pay attention to this concept. That's when we do the TS diagram, so you understand that. Now, we have, oops, I put the Q out in the wrong place. Now, here at the source, let's say for the sake of argument, we have 20 degrees Celsius water coming in. Now I'm extracting steam coming out of the turbine, let's say at 200 degrees Celsius. I recover the heat and it comes out, same mass, but it comes out in a lower temperature because I recover that heat. So let's say this is 80 degrees Celsius. So I'm mixing the 20 degrees Celsius with 80 degrees Celsius. What would be the temperature here? If you average it out, this would be like, 50 degrees Celsius, right? So when you look at this too, you see that 0.4 on the TS diagram going to be between between 0.2 and 0.3, right? Again, all these numbers are just I made up. I'm doing this for you to understand where that 0.4 is going to land on the TS side. This is 20 degrees, it mixed with 80 degrees, and then we have an average it out of, let's say, 50 degrees coming out. So if this is 20, this is 80, this point is between 0.2 and 0.3 on the TS side. Do you have any question on that?
Sorry, I have a question. Is the condenser not requiring any work in, or is it Q out in the condenser?
That's a Q out on the condenser.
There's no work being provided to the condenser?
There is never work on the condenser.
Oh, got it. Thank you. Oh, sorry. I got it mixed up. Sorry.
No, that's okay. There is no need to be sorry. You need to remember the fundamentals, the basics of the, this cycle. All the work, which is compression and expansion, happen isentropically. All the heat addition and heat rejection happen at constant pressure. This is the heat rejection, constant pressure. So at constant pressure, we cannot do any work. We're just adding heat or releasing.
I got my words. I got it confused with compressor and condenser. I'm sorry.
No, don't be sorry. No big deal. No big deal at all. So that's the whole concept. So I'm going to erase all this thing that I put here because these are all nonsense. It's just for you to understand that. Now, in order to do the TS diagram, all we need to do is just follow the diagram and you see how easy it is. My point 1 has always been in the saturated liquid line going up to point 2. This is my point 3. That is where it enters the open feed water heater. And look at my point 4. Point 4 should be between 3 and 2. So a little bit more exaggerated. There you go. So 0.4 is somewhere around here. Not exactly in the middle, but somewhere between 0.2 and 3. Now 0.4 is the base of the second pump. So I'm going to go up for the second pump. You get to 0.5. Then this is 0.6. Now, in order to find 0.7, this is 0.8. The last point always going to be in a mixture. So I draw the line parallel to S-axis. This would be my 0.7. So that's the TS diagram. The trick is we always have the base of the pump located at saturated liquid line. But this time, as you can see, the base of the second pump is not located at saturated liquid. It's between 0.2 and 3. And you see this relationship? Through this relationship, we find the value of H4. Once we find H2 and H3, since we already have the values on M2 and M3 and M4, we can easily find the value of H4. That's the reason we need this relationship. What goes in this box is equal to what goes out. M2, H2 going in, M3, H3 going in, M4, H4 going out. This is a relationship. We can find the quality, we can find the value of H4. The rest of it is very routine that we always do that. Now, if I transfer everything here to my TS diagram, as always, this is the condenser pressure. This would be the boiler pressure. Oops. Yeah, right. And this would be our Q process pressure, which our Q process pressure is the same as open feed water heater pressure. Now, pressure 1 and 8 are the same. Pressure 2, 4, 3, 7 are the same. Pressure 5 and 6 are the same. So here, we have P2 equal to P3 equal to P4 equal to P7. The same pressure mark. Pressure 5 and 6 for a boiler is obvious. Pressure 8 and 1, the condenser pressure is very obvious. Any questions?
Professor, please, what's the pressure between 3 and 7?
Between 3 and 7 is called, that's the pressure of the process heat.
Thank you.
That's the pressure of process heat. See, between 7 and 3, 7 and 3, that's this QP process pressure. Any other questions? Well, to understand it better, let's do an example. So here, the boiler pressure is 7 megapascal. And pressure of the condenser is 10 kilopascal. And this pressure is 600 kilopascal. That's why 0.7 is outside and superheated. We always want that 0.7 to be in a superheater so we can get a better system rather than having 0.7 down below here. And here I have S6 equal to S7 equal to S8. They're all in the same isentropic line. S1 and S2 are the same, S4 and S5 are the same. So a lot of people make a mistake on a quotient and put this right there and say 0.3 and 4 are this in the same place. That's not true. So be aware of this. If you make that mistake, everything you do from that point on, it's all going to be wrong. So you need to pay attention to that. Now, let's see, temperature at 0.6. Is 500 degrees Celsius. And now, mass flow rate. Okay. The mass flow rate is given to be 30 kilogram per second. So if we assume this is 1 unit, so that would be the mass flow rate, 30 kilogram per second. Then the problem says we use 25% of the mass going to the feed volume. So the 25% of 30 would be 7.5 kilogram per second coming that direction. The balance of it, which is 22.5 kilogram per second going this direction. So as you can see, now I have all the mass flow because of all of these relationships. M7 and M3 are the same, so this is 7.5, 22 and a half, 22 and a half, 22 and a half, plus 7 and a half becomes 30, 30, 30. Very simple. Again, I don't expect you to memorize any of these that I write down here. It's very easy, common, sense what is happening here. Do you have any questions? Okay. Now, if you're done with this diagram, I want to erase that. Just let me know when you're okay. This would be equal to M6, M5, M4. Now, M7 is equal to M3 is equal to 7.5 kilogram per second. M8 is equal to M1 is equal to M2. That is equal to 22.5 kilogram per second. So if you write these things down, once you're given the mass flow rate, based on your diagram, if you write that so you know you're okay, the only other thing you need to write the energy balance equation. And the energy balance equation, in this case, would be this. That's what we need later on to find the value of H4. So are we okay? Should I erase the diagram or you still want it?
I think we're
We're
good.
good.
Thank you.
What was it? You're okay?
Yep, we're okay.
Yeah.
Now, to solve this problem, as always, I'm going to start at state 1. I have P1 equal to 10 kilopascal. X1 is equal to 0. Going to saturated liquid table, I find H1 and V1. Kind of memorize this number because we always use the condenser pressure as 10 kilopascal. Once you solve so many of these problems like that, just stick in your memory. So that's the pressure and the volume. At state 2, I have the work of a pump. Let's put them here, work of the pump 1, work of the pump 2. This is my Q in. This one is my Q process. This is the Q out. Work of the turbine 2. Work of the turbine 1. So I have work of the pump 1, which is equal to H2 minus H1, which is the same as V1 times P2 minus P1. From here, I can find the value of, excuse me, H2 to be 192.41 kilojoule per kilogram. Now I go to state 3. I have a pressure of 600 kilopascal and X3 is equal to 0. So from there, I can find the value of H3 to be 670.38 kilojoule per kilogram. Now comes to state 4. At state 4, I have to use this relationship in order to find the value of H4. So I have M2H2. What is my M2 value? Is 22.5 kilogram per second times H2 plus. My M3 is 7.5 kilogram per second times H3 has to be equal to M4. What is my M4 value? When it comes to 0.4, what do I have? Anyone?
30.
Yes, very good. Because I wrote it down up here, that's our value. I have H2. I just found H2 and H3. The only unknown is H4. So from that, I will find the value of H4 to be 311.9 kilojoule per kilogram. Now, as you can see, the value of H4 is between H3 and H2. It's bigger than H2, but it's less than H3. That's what it's supposed to be because its temperature is lower than temperature at 0.3, but it's higher than the temperature at 0.2. That's how you can check your calculation all the time. See if you're doing the right thing or not. Now that I have this, I go to the table and find the value of V4 corresponding to this H4. Why? Because 0.4 is the base of my pump and I need that volume. I cannot use V3 because V3 is not the base of my pump. V4 is the volume for the base of the pump. So that's why we find the H4 from this relationship. Then we go to the table and find the value of V4 corresponding to that. That would be 0.00126 meter cubic per kilogram. So now I go to state 5. State 5, I have a local pump 2, which is equal to H5 minus H4, which is same as V4 times P5 minus P4. P5, it's 7,000 kilopascal. P4, 600 kilopascal. V4, I just looked up the table and found it from there. H4 value, I calculated from energy balance equation. So very quickly, I can find the value of H5 to be 318.87 kilojoule per kilogram. That's my H5. Now I'm coming down to state 6. State 6, I have P6 equal to 7 megapascal and temperature at this point is 500 degrees Celsius. So I go to superheated table and I find H6 and S6 on superheated table. This becomes 3411.4 kilojoule per kilogram. And the value of S6 is 6.800 kilojoule per kilogram degree up. Go to state 7. I have P7 equal to 600 kilopascal and S7 equal to S6 equal to 6.8. Again, I go to superheated table and I find the value of H7 to be 2774.6 kilojoule per kilogram. That's H7. At state 8, I have P8 equal to 10 kilopascal and S8 is equal to S6. From there, I will find S of F, S of F of G, H of F, and H of F of G. Now, H of F is the same as my H1. That would be 191.81. Now, S of F is 0.6492. S of F of G is 7.4996. And H of F of G is 2392.1. I get all these values from the table. Now I can say X8 is equal to S8 minus S of F divided by S of F of G. This will give me a value of 0.8201, and H8, which is H of F plus X8 times H of F of G, that will give me the value H8 to be 2153.6 kilojoule per kilogram. That's my final H value. Now, there is a specific things that you need to pay attention. We said the reason we're doing cogeneration because we want to get two products from our cycle. One is the power, that's where we get it from here to convert it to electricity. The second one is the Q process. So we need to calculate this Q process. So now, Q in would be the mass of M5 times H6 minus H5. M5 is 30 kilograms. I have H6, I have H5. This will give me sorry, this is a dot. 33,477 kilo. That's my Q. My Q out let's do the hardest. When W of the pump total is work of the pump 1 plus work of the pump 2. The work of the pump 1, the mass flow is 22.5 kilogram per second times H2 minus H1 plus 30 kilogram per second times H5 minus H4. That gives me the total work of the pump. The value of the total work of a pump will be 210.6 kilowatt. I made an error here. This is not the Q in. The equation and everything was right. This is the total work of a turbine. Total work of a turbine is a first turbine, which is M6, it's 30 kilogram per second times H6 minus H7 plus 22.5 kilogram per second, that's a balance of it, times H7 minus H8. That value becomes 33,477 kilowatt. I have the total work of a turbine, total work of a pump. Now, what I do, I get the net work, which is total work of a turbine minus total work of a pump. This gives me the net work of 33,866 kilowatt. Now I need to find two more values. I need,
Excuse me, Professor.
yes,
Could you repeat what the numbers are for the work pump
Sure.
of total?
not a problem. Work of a turbine is a mass of H6, which is 30 kilogram, times H6 minus H7. Now, the second turbine, which 7.5 goes this way, 20.5 goes the other way, so that would be 22.5 kilogram per second times H7 minus H8. If you partner H6 and 7 and 8 into that equation, you end up with 33,077 kilowatt. 33077. For the pumps, the first one is this 22.5 involved in it. So 22.5 times H2 minus H1. This is, see that 22.5, M1, M2, M8, they all have this. So M1, which is 22.5 times H2 minus H1. And then from 4 to 5, M4 is 30 kilogram. That would be 30 kilogram times H5 minus H4. You end up with 210.6 kilowatt. Yeah, I told you that work of a pump is so small compared to work of a turbine. 33,000 versus 210.
Thank you, Professor.
No problem, no problem. Now, my network would be the difference between the two, and that would give me 32,866 kilos. Now, is it okay if I erase the top portion of the left side?
Yeah,
Yes.
Okay. Now, I need to find the Q in, and also I need to find the Q process. My Q in would be M5 times H6 minus H5. And 5 is 30 kilogram. If I plug this number in, I will get the value of Q in to be 92,000. $788 kilowatt. That's my Q in. Now I want to know how much heat I'm generating to send it out of the cycle for another process. So therefore, I need to have the Q process. What is the Q process? Between 0.7 and 0.3. So that would be M7 times H7 minus H3. M7 is 7.5 kilogram. I have H7, I have H3. If I plug everything in, I will get the Q process value of 15,872 kilowatts. So not only we found the network and we found the Q in, we also have to find the Q process. Now, this is where everybody making mistakes, and I didn't want to talk about it until now. When we had a power cycle, we had one product, and that was a network. We divide the network by the amount of heat you put into the cycle to get thermal efficiency of the cycle. Now, we cannot get a thermal efficiency because now we have two products. We have a network, that's one product. The second product is our Q process. So we need to include that. Therefore, we no longer have thermal efficiency for cogeneration. What we have, it's called let me remember what the book called it. Oh, the book called it utilization factor. I call that cogen effectiveness. Whichever you want to call it is fine. The utilization factor we showed with epsilon, and there's a U here, and that is equal to desired output divided by heat going into the system. Now, what is our desired output? We have two of them. So the effectiveness or utilization factor epsilon is equal to W dot net plus Q process divided by Q in. This is not thermal efficiency. Because thermal efficiency, our desired output was a network divided by Q in. You can see the difference. So this is absolutely not thermal efficiency. Don't make a mistake. When it comes to cogen, since we have two products, we add both of them together, then we divide it by Q in. Do you have any questions? So don't make that mistake. Every semester, one or two students will make that error and say the thermal efficiency is the network divided by Q in. Or they say thermal efficiency is network plus Q process divided by Q in. That's not true either. Because when it comes to cogen, we don't have thermal efficiency. Please pay attention to that. So now that I define the utilization factor, I have the network, I have the process heat, and I have Q in. So by plugging all these numbers, my network is 32,866 kilowatt plus 15,872 kilowatt divided by 92,788 kilowatt. So the units cancel each other out because they're not supposed to have a unit. And that epsilon becomes 52.41%. That is the effectiveness of our cogen plant. Any question? Please, if you have any question, ask, because this is important. Comes to your final exam, and I don't want any surprises or any confusion.
Excuse me, Professor.
Yes. what is
So
it?
it's so for this, the effectiveness is gonna be the desired outputs over the heat input, or
That's a heat input right there.
Hmm.
That's a Q in. That's our Q.
Okay.
I replace what I wrote here with all these values. My desired output are two of them, network and Q process. What I'm putting to the system, the amount of heat, is my Q in. Did that answer your question?
Yes, Professor. Thank you.
Okay, no problem. Anything else?
Was just curious if we had a kind of cogeneration plant on our campus anywhere.
Yes, we do have a cogeneration in our campus. I don't know if you can go see it now, but you can try. Go see the facility guys. The cogen plan is right below the administration office towards, engineering, area. And you can tell them that you're a student, mechanical engineering, and taking power plant design, and you want to see our cogen plant at the campus. Before, all of the students went there and looked at it, but I don't know because of the pandemic, they're going to do it or not. It's worth a try.
Got it. Thank you.
No problem. Any other questions?
Yes, Professor, you said there's no thermal efficiency?
Yeah.
No therm, okay.
There is no, because again, if you remember, the whole concept of the thermal efficiency we had, our thermal efficiency was desired output divided by heat input. Our thermal efficiency, we have only one output, and that was the W net divided by Q in. This is two different things. So there is no thermal efficiency for cogeneration because we have two outputs, not one. All the cycle in chapter 9 and 10, we had only network as our output and the Q in as our input. We divide the output, but by input, we got the thermal efficiency. We're doing the same thing, but in this case, we don't call it thermal efficiency because we have two outputs here now. So it's a different ballgame. That's why we have effectiveness or utilization factor, whatever you want to call it. So don't mix these two together. Totally different. We don't have this for the cogen plant. It works everywhere else, but not the cogen plant. Any other questions? Now we have only one part left, which is a combined cycle, but we don't have time to do that. But I'm going to do something, and I want you to pay attention because that also could be on your final exam. Let me erase this part so that gives time for you guys to write all of this. Now, what happens if I create a cycle that is reheat and regenerative together in one cycle. Let me know when you finish this so I can erase it.
I think we're good.
Yeah.
All right, great. Now, we talk about reheat. We can have one or two reheat in one cycle. We talk about open feed water heater. We can have one or two of them. Forget about closed feed water heater. They're not going to be in your test. Now, we talk about cogen. What about if I combine these two together? Now, I'm going to show you, I'm going to set it up, but I expect you to go on your own, solve that problem. Let me know if you have any questions. This exercise will help you to understand this concept better. In case you have it in your test, you're not lost anymore. So here's our boiler. First turbine, I extract from the turbine, coming back, reheated, going the second turbine. At actually T2 and T3. Now I come up here, go to open feed water. And then the balance of it goes to the condenser, come to the source, pump one, going to open feed water heater, coming out of feed water heater, second pump, and going back to boiler. This is point 1, point 2, 3, 4, 5, 6, 7, 8, 9. Okay? Now, if you ignore this, what do you have? You have a regular open feed water heater. If you ignore that, you have a regular reheat cycle. So it's nothing strange and nothing that you haven't seen. Gas diagram, very easy. Again, as always, when we have an open feed water heater, this would be Y, this would be 1 minus Y. Keep in mind, this is 1 unit, comes here, goes in, no changes there, come back up, still 1 unit. Then at point 8, I take a Y out, and the balance goes that way. So that's 1 minus Y. Here, 1 unit, goes up all 1 unit. Okay? Now, the TS diagram, I follow this. Okay? Easy. 1 and 2, first pump, going to 3, my feed water heater, second pump, 0.4, This is 0.5. That's 0.6. 5 and 6. This is for the first turbine. I reheat it back to 0.7, same temperature there. Now from 7, I go to 8 and 9. This is my 0.9. This is 0.8. Very simple. If you didn't have a feed water heater, you would have coming down here going reheat and go straight down. Now that we add the feed water heater, it's just, one extra line here. So that's a reheat and regenerative cycle. So in this case, this is the Y, this is 1 minus 1. Now I have 3 turbines, 2 pumps, one Q of the boiler, 1 Q of the reheat. So this is my Q of a boiler. This is the Q of a reheat. Condenser pressure, feed water heater pressure, boiler pressure, and here, if you look at it this way, that would be the reheat pressure between 7 and 6. Now, let's say if this is 600 kilopascal, this is 10 kilopascal, this is 7 megapascal, T5 is equal to T7 is equal to 500 degrees Celsius. And the reheat pressure is 1 megapascal. The reheat pressure is 1 megapascal. Find the thermal efficiency of that. Now, I want to teach you something. I want you to pay attention. Are you done with this diagram?
Yes.
Okay. Now, if you remember the first day of the class, I said, try to throw out that hat that you're wearing as a student and start replacing it with I am engineer. The difference is when you're an engineer, you have an engineering thought process. And you have to put it in this piece of paper to communicate with a third party. With your student, all you care is crunching your numbers. And that's the mistake you did on the first test. And some of you paid for it dearly. Let's hope that it won't repeat it again. Now, I'm not going to solve this problem, but I'm going to set it up. This is what you should do always, because it will help you a lot. Now, just pay attention. State 1, I have P1 equal to 10 kilopascal, and I have X1 equal to 0. I go to liquid side, I find H1 V1. I leave it there. I don't even look at the number. Just leave it there. State 2. I have work of a pump 1 equal to H2 minus H1, which is equal to V1 times P2 minus P1. Therefore, I can find H2. I leave it there. And state 3, I have P3 equal to 600 kilopascal, and I have X3 equal to 0. I find H3 and V3. At state 4, I have work of a pump 2 equal to H4 minus H3, which is the same as V3 times P4 minus P3. From there, I can find H4. At state 5, I have P5 equal to 7 megapascal, T5 equal to 500 degrees Celsius, superheated table. I will find H5 and S5. At state 6, I have P6 equal to 1 megapascal and S6 being equal to S5. Again, superheated table, I will find H6. At state 7, I have P7 equal to 1 megapascal and P7 equal to 500 degrees Celsius. I find H7 and S7. At state 8, I have P8 equal to 10 kilopascal and S8 is equal to S7. Now I will find S of F, S of F of G, H of F, H of F of G. Once I have this value, I write X8 is equal to S8 minus S of F divided by S of F of G. I will find the quality X8. Once I find that, I write H8 is equal to H of F plus X8 times H of F of G. So I find H of 8. That's all my H values. Now, please pay attention. This is to learn how to manage your time. That's your future. That's your engineering work. That's your engineering thought process. Look at state 1 and 3 and state 9. I mean, state 8. Where are you? What are you looking at? You're looking at the saturated liquid table. If you write everything down, all you need to do, find H1 and H3, V1 and V3. While you're in the liquid table, also find S of F, S of F of G, H of F, H of F of G. Because you're going to need it later. One shot through one table, one time, finding H1, V1, H3, V3, S of F of G, H of F, H of F. Once you find those, then you go to superheated table. Look at this. You have 1, 2, oh, I'm sorry, that should be 0.9. and miss state 8. State 8, you have P8 equal to 600 kilopascal, and S8 is equal to S7. Again, superheated table, you find H8. So all of this should be 9. None of you caught that. So as you can see on the superheated side, I have 0.5, 0.6, 0.7, and 0.8. One shot, I go to superheated table. Based on this temperature and pressure, I found H5 and S5. Based on this information, I find H6. Then I find H7 and S7, and then I find H8. All in one shot, without going back and forth to the table. That is the time management. You save tons of time that way. So that's the important part. Once you have all of that, then you start calculating. Plug in the number, find H2. Plug the number here, find H4. Plug the number here, find the quality. Plug the number here, find H9. All you need to do 4 times doing the calculations. The rest of it, twice you go to the table. Once on a saturated liquid, once on a superheated. You're done. Simple as that. Once you've done everything, your Q in total would be Q of the boiler plus Q of the reheat. That means H5 minus H4 plus H7 minus H6. Your Q out would be 1 minus Y times H9 minus H1. By the way, we forgot about the Y, and that is basically summation of all energy. That would be M8, H8 going in, plus N2, H2, that will give you N3, H3. This is Y times H8 plus 1 minus Y times H2 is equal to 1 unit times H3. That's how you find the Y value. That's Q in, Q out. Your thermal efficiency, 1 minus Q out over Q in. I set the whole thing up for you. Now do yourself a favor, go through this exercise, do what I said you should do, and see how fast you can solve a problem that has 9 H values and 1 parameter Y that you need to find. And see that you can solve this problem in 20 minutes. But if you're not prepared, this will call you, you can spend an hour time and still being lost. So do yourself a favor. It's already been set up. All you need to do, go to the table and find the values. And tell me next time, what did you find? I already took 10 minutes or 5 minutes of your time. Sorry about that. For those of you who want to talk to me and stay, from office hours, you're more than welcome to do that. And the rest of you, I'll see you on Monday morning.
All right, thank you, Professor.
No problem, my pleasure.
Professor, can you scoot to the side, please, so I can see the entire board?
I'm
Thank
sorry.
you.
Whoops.
Professor, it's just, can you give me the temperature of state 7, please? It's a little small.
500 degrees Celsius, 0.5 and 7.
Got it. Thank you.
No problem.